So let's continue with our topic on hashing, which we began last week. So we looked at how to implement hashing in Rust. And today we want to go a step further, this time to look at how to hash to groups. In other words, supposing you have an arbitrary size of text, how do you map it to elements of a group? So that is what we'll be looking at today. So in today's lesson, of course, we'll begin by looking at how to hash to an additive group, mod n. So supposing you have, let me say this group, Z4, for instance, and we know the elements of this group are 0, 1, 2, and 3. So what we want this time is, if you have an arbitrary text, how do you hash it to one of these elements randomly? In fact, that is of course to ensure security of your data. So we don't want to, we are not hashing it to each of the elements, but just to one of the elements at random. So you might want to hash your text and map it to 3, for instance, or you want to map it to 2, or want to map it to 1, but we want to do it randomly so that an adversary may not be able to tell what our text was. So generally we begin by, first of all, define what hashing to groups is. Then after that, we go to specific, we look at additive group and then multiplicative group. I've said that this procedure is critical in cryptographic schemes, including pairing-based cryptography, elliptic curve cryptography, which we'll be looking at later, and then the zero-knowledge proofs, which you again will be looking at later. Now, what do we require to do? What is our problem? Our problem is we want to ensure that the output, that is, if you have the input and the input is an arbitrary text, a very large text, for instance, want to ensure that the output that comes out after inputting that text is distributed across the group. You distribute it across the group. And I said that would be random. You do it randomly. Although we can calculate manually to see where the text will be going to, which element, but that process is tedious, so we'll just be using Rust to do that. Now, so how do you define hashing to a group? So assuming that we have a group G, assuming that G is a group, and we have this arbitrary text or arbitrary data that we want to hash. And then the hash function would be a function h, which maps the elements of this group. This arbitrary set, which maps this arbitrary set to the group. So the elements of these elements are mapped to the elements of the group. So what I mean here is that you had a text, this text converted to a number of a group. Is that okay? Because the group has numbers. The group, for instance, our additive group has numbers 0, has 1, has 2, has 3, and so on, up to n-1. So this text, which you have, we convert it to one of these numbers. That is for security reasons. Is that okay? And we say that so that after we convert to those numbers, we don't require the text. We don't require the text. What we require is that number. So that if anybody was to come and check and want to see what our text was, the person will meet one of these numbers and will not know what our text was. Is that okay? That is for security reasons. And I said, of course, that is how the internet works. If you have to go to open your account, for instance, the Gmail account, and you are inputting your password is hashed to some data. Is that okay? is hashed some data. So supposing your password was 2050, maybe your password was 2015 at A. So that is your password. So that is what you input when the email asks you to input your password. That's what you input. But once you input this, the system converts this to hashes it. The system would hash it, convert it to something else. And then it deletes what you entered, your raw data. Is that okay? So your raw data is deleted. In other words, anybody coming later will not be able to find your raw data, will not be able to find the password you input. But then after the system converts this password to the hash, a certain digit, it stores that. So that next time when you come, you are told input your password again, you just input the password and that password again is converted to a number. If these two numbers are the same, the system is able to recognize it's you. But another person coming, since this other person does not have your original data, will not be able to access the account. So that is what is happening here. This time we are converting data to a member of a group. The group and elements. So you have a text, for instance, a text that says, let's meet for a class at noon. That text is hashed and then converted to a digit mod n. Converted to a digit mod n so that anybody else will not be able to see that and understand what it is. Now, some want to do hashing to additive groups at this time. Then next we look at how to hash to multiplicative groups. The steps are almost related, only the calculations that are vary because in one set, we have the additive group where we have 0 as one of the elements, the identity, the other one has no 0. So the calculation changes a bit, but the steps are the same. Now we know what an additive group is mod n. We've said that these are groups comprising of elements 0, 1, 2, 3, all the way up to n minus 1. All the way up to n minus 1. So if you have Z7, the elements will be 0 to 6. All the way up to 6. So then how do we hash to this group? How do we change our text to numbers of this group? That is what we want now to find out. That's what we want to find out. Of course, we'll be using SHA-256 that we looked at last time. So again, is the one we'll be using this time, but just a slight difference. The code will almost be the same. We just vary a bit to ensure that the elements are converted to a group. You remember SHA-256 was converting the text to hexadecimal that 60, was it 64 digits? 64 digit number, is that okay? Hexadecimal. So what we'll be doing this time, first of all, we do SHA-256. SHA-256 would convert this text to a very long 64-digit hexadecimal number. Then this hexadecimal number is now the one we convert to an element of the group. So that will be the steps. So the first step, we'll just do the SHA-256, convert this text, the text you have, to hexadecimal digit. So I said compute. So the first step I've said is that we shall compute the cryptographic hash using SHA-256 on the input. So that will give us a result, and this result will be a hexadecimal number. Of course, it will be 64 digits. And then This hexadecimal number, we will now convert it to an integer. So you see the steps, convert it to an integer, what we're just doing, and that's what we learned. That's what we learned earlier. Earlier on, we had learned how to convert binary numbers to decimal numbers, and then converting decimal numbers to hexadecimal numbers. So what we do here, SHA-256 gives us a hexadecimal number. Is that okay? This hexadecimal number we convert it to decimal number, mod n. So when you convert to a decimal number mod n, you have a number of the group. You have an element of the group. And that's what I've said here. That's what I've said here. What I said here is the hexadecimal number coming from part A is converted to an integer. And what I mean by this is that we are converting this to a decimal number. Is that okay? Then after converting this to a decimal number, we now reduce it mod n. You reduce it mod n. So when you reduce it mod n, you have a member of the group. You have a member of the group. So those are the steps that we'll be doing. So it's not a very difficult thing, even doing it manually, only that the steps are many. Is that okay? The steps are many. For instance, when you're converting that hexadecimal number, and it's a 44-digit number, so when you're doing it manually, it will take you long. So that is why I avoided the steps, manual steps, because you are dealing with a very long number, and the hexadecimal. Of course, we know that to convert it to decimal, we know the steps of doing that. We can also have, so if you have two codes, if you have a code that we did last time, the one that hashes using 256, then you have a code that we did earlier, the one of converting numbers from decimal to hexadecimal and back. You can do that. Is that okay? You can do that. But now you can also write a code that combines all these two together. And that's what we'll be doing in today's lesson. So that we combine, we have one that is doing the hashing, and then one that converts that hash to a decimal number. And then of course we add an element that reduces mod n. So those are the things we'll be doing. But basically, we already know what we're supposed to do. If you have two different codes, you'll still get the same result. You have those two different codes. Now, so how does it work? How does it work? Of course, I'm just repeating what I had said. Now, so instead of receiving the standard hash after using SHA-256, we were supposed to get an element of the group and utilize this element of the group later. Is that okay? Yes. So that's what we'll be doing. That's what we'll be doing. So if I have all this text that I have, all this message that I have, and I want to store it, I want to send to her, I may convert all this text to one number, so that the recipient may be able to know what the message was, but any other person that is not, the message is not meant for that person, will not be able to tell what my message was. So that is what we'll be doing. So the first thing you do, I'm just repeating, you hash the entire message using SHA-256. But you can also use another algorithm. It's not necessarily SHA-256 only. You can use any other. Is that okay? We are using SHA-256 because we noted that SHA-256 is secure, is very secure than the others. It's not the only one which is secure, but it is secure. And of course, it's commonly used. So we hash that message. A standard hash, we can use this standard hash to SHA-256. SHA-256 will take this message that you have, the data that you have, and output a hexadecimal number. Is that okay? We'll output an hexadecimal number. That will be the output. This output is just a number, and it may not be very much necessary. So what we want is to ensure that we we add more security to our information, we add more security to our data. So now to add more security to our data, we hash to a number of a group, just adding layers of security to the information. So I've said after hashing the message, the result must be mapped or transformed into an element of a group. So it's transformed into an element of a group. Now, this is very important, especially when we begin looking at elliptic curves. The elliptic curves, we're talking about groups, points on a group. Is that okay? And you have a message, and this message, you need to convert it to a point. Is that okay? So you see, the points of elliptic curve are considered to be a group. They form a group. So that's what we'll be doing, of course, when we reach there. When we begin elliptic curves, of course, I'll show you again how to convert message to points. And this is one way of doing that. This is one way of doing that. You hash to a point. Now, so my reasons, why do we hash to a group? Somebody might ask that. Why should we hash to a point of a group? And I've said the first reason is security. So we just hashing to a point of a group to ensure that the data that we output will be more secure and therefore can be used for encryption, can be used also for key exchange, and can be used for digital signing. So before you do all of this, before you do encryption, of course, last time I said when you are doing encryption you don't encrypt the data. Don't encrypt the data that you want to send. What you encrypt is the hash. Is that okay? So the hash is what you encrypt. So that's what we've been encrypting, not the real data that we're supposed to send. So after encrypting the hash, then that hash together with that data you send to the recipient, and then when the recipient receives the data and the hash, the recipient will also want to hash this data and see what he gets, and compare what he gets against what you send as the hash. If they're the same, the recipient is able to tell that the data he has received from you is genuine and has not been corrupted. Now, so the first reason why we hash to a group is security. The other one is uniform distribution. So I've said that these hash functions are intended to produce results that are uniformly distributed across their range. Of course, I said this will be random. So hash function will be doing it randomly without bias, without being biased on some numbers. It just does randomly, chooses a number randomly, and so on. So the output behaves randomly within the group, which is critical for avoiding bias that could compromise security. Now, you see, you see the issue of doing randomly assists to prevent a lot of attacks. For instance, when you're talking about the attack where somebody wants to try all the possible possibilities, which we call the brute force attack. And if you have done it randomly, it becomes hard for the attacker to try and find what the original text was. Now, an example here. Of course, I've used an example in a multiplicative group, but I'm dealing with an additive group. Now, just an example to illustrate what we'll be doing. Suppose you have the message, hello friend, and this is the message you want to send to somebody. Is that okay? And I want this message to be converted to an element of a group. So the first thing I'll do, I'll hash this text using SHA-256. And SHA-256 will produce a hexadecimal number. To produce a hexadecimal number. So I've done the first step. The first step is to hash it using SHA-256. Then I would map it. That's the second step. I would map it to an element of a group. So that means I transform this to an element of a group. And of course, we are using prime numbers. It's easier to use prime numbers for the groups. And then the second thing I will do after I have converted to an element of a group, I want to reduce it more to something. But there's something I've said here, that this ensures that the number is within the set of elements. So when you hash to an element of a group, if the group has elements 0 to, let me say, if it's multiplicative, it has elements from 0 to n minus 1, elements which are relatively prime to n. So this will ensure that the text becomes one of the elements here, becomes one of the elements within that. Now, this process will be very important in what we call discrete log problems. It will be very important in discrete log problems, and we'll see how important it is. So G here is the generator. So if I wanted to hash, what would I do? What I will do, suppose I wanted to hash manually. Let me just show you how it will work manually. I have this group. Let me say the group is Z7. The first thing I will do, I have done the hashing. Is that okay? I've done the hashing, so I have that hexadecimal number. Now, to convert this text to a member of a group, first of all, I have to identify the generators of that group. The generators of that group, and those are the ones I've called G here. G is the generator of the group. Is that okay? So supposing the group has 4 generators, I may be interested with only 2 or 3, or even the 4. But let me say, supposing I have generator 1, I have generator 2, I have generator 3, I have generator 4. And this is an additive group. And then I have the text. And I want to convert this message to, let me say, 1, 2, 4. And these are elements of the group Zn. These are members of Zn. So for me to convert this message here, what I'll do, I take this generator, I raise it to 1, this generator raise it to 2, this generator raise it to 4, and supposing I have another element that I want to map to, and so on. So that's what I'll be doing. If you are doing it manually, that's what you'll be doing. If you have to do it manually. But it's a bit tedious if you attempt it manually. So this I've said because it's applying the discrete log problem, we will then apply it in Diffie-Hellman key exchange or digital signatures. That is where we can then use this knowledge, among other uses. Now, after you've converted the message to a member of the group, the question is, does the message get stored as a group element? Does the message get stored as a group element? Because you had a message, and then you converted to an element of the group. So does it get stored as a group element? And the answer is yes. The answer is yes. So after you've hashed, the message is supposed to be represented as a group element. This is what we will use for future cryptographic operations. For instance, if you wanted to sign, what you will then be signing is that group element. You sign on that group element. You don't require to sign the original message. Is that okay? Yes. Because we are assigning the hash. We are signing on the hash, not the entire message. I've said because you are dealing with the group element, a representation of the original message, it is no longer necessary to store the original message. So you don't require the original message. You only require that group element for storage. So that if somebody was to come and look for your laptop and wants to see and find out what you've been discussing, that person will get group elements. And on getting group elements, the person will not be able to understand what they mean. Now, the following Rust program demonstrates how to hash an input to an additive group using SHA-256. The resulting hash is then reduced to mod large prime number. And there's a reason for large prime number. We've already explained that. To ensure security, of course. To ensure security. So we use those large prime numbers. You see large prime numbers, what it means, if my group mod n, if n is large, that means then I have so many elements. Is that okay? To map to. I have so many elements to map to. So since I'm mapping randomly, the hash would take any of those elements randomly. And it means that our adversary or attacker may not easily be able to identify which element. Because there are so many elements and they were chosen at random. So this attacker may not be able to tell. And that is why we require those large prime numbers. Now, so you can see my dependencies. These are the dependencies. You have SHA-256. You have the big integer or big unit, and we have the num traits. The last two, we've been talking about them, but the SHA-256, we talked about it. This one is the one that is just hashing the original hashing using algorithm 256. So that is what it will do. That's why we have to import it here. Now, so we have two functions. We have this function, hash to group, and then we have the main function. Of course, I'll explain what each of these does, and of course, I've written some short notes just to guide us, but I'll explain what they do. But first, let's look at the code and see how it runs. Now, so here is the code. This is the code. Come to the main function. I want to hash this sentence, hello world. And my prime number that I'm using, the large prime number is here. This is a large prime number I want to use. I want to hash to an additive group. So I want this text to be converted to a member of the group. Is that okay? So let's try and see what it gives us if we were to run it. Now, this is the element of the group. This is just one element. This is just one element of the group. This is what has been hashed. Let's use a smaller group so that we can see. We are using, let me use mod 7. use mod 7 and see what we get. Because it must be a member of that group. It has been hashed to 0. When you use mod 7, it has been hashed to 0. Is that okay? So it's a member of that group. Can try and hash it to 17. 17 is also a prime number. Let's see where that message will be hashed to. This message has been hashed to 11. It has been hashed to 11. So it must be a member of that group. So we are taking a whole text, and this text we are converting to a member of the group. Is that okay? So supposing you have security problems with the government, and the government was to come and check your laptop. Normally they come for your laptops and carry to the DCI. They'll find there 11. When they find 11 in your laptop, they are not able to tell what that 11 is about. There is a lot of communication. Is that okay? That 11, that is what you store. There's a lot of information. Let me see if I was to add some text and still hash it to. We say that any small change will change the hash. Is that okay? You expect this hash to be different? Let's see. It has been hashed to 3. This one has been hashed to 3. Let me remove this exclamation mark and see where it will be hashed to. That's a small change. Of course, the problem is that we have few numbers. Mod 17 has few numbers. So it may have some text being marked with the same number, because those are few numbers. This one has been hashed to 15. Is that okay? Yes. So that is what we say. If you are to send your hash together with your text, and the person receives and then hashes it, when he finds that there's small change, he can be able to tell that this is not the original message. He can be able to tell that somebody tampered with it along the way. Hashed to. Yeah, you see, so we have the generators. Those generators, this is an additive group. So G1 raised to X plus G2 raised to Y plus G something raised to something. The result to, when you add, you get one value. Yes, so that's what is happening. And we'll be using that, what we call, we looked at homomorphism the other time. Is that okay? So if the group is additive, we expect that, so let me just write this. So we are hashing to members of the group. Let me say the members of the group, G1, G2, G3, and so on. So if the sign is additive, the group is additive, expect that the result will be added. So what you get when you hash there, supposing you get that, the result, you add the results. Is that okay? You add the results, and when you add the results, you get just one element. That one element is as a result of all those. You've added this plus this plus this plus this, then you get one element. Of course, when you add this, then finally you reduce it mod n. The result is reduced mod n. That was your question, eh? Okay. The hash that we created, that one G is our maybe one. Yes. Hash that we Oh, yes, yes, I get your, let me just clarify there. Thank you for that. Now, I used SHA-256. That's what you're saying, yeah? SHA-256 gave me a hexadecimal number. This hexadecimal number is a very long number. Is that okay? This number, I'll divide it. If I want to use 3 generators, I divide this hexadecimal number into three parts. Is that okay? So supposing this was 256, let me say, supposing it was 128 bits. 128 bits. If I, no, it's two, of course it's 256. 56. So if I divide this by 2, what do I get? I get around 139. Eh? So if I want to use 2 generators, I would cut this into 2 bits, or 2 parts, where one part is 139 bits and the other part is 139 bits. Is that okay? Yes, you just cut it into 2 parts. And if you want to use 3 generators, you're cutting it into 3 parts. So one part you call it X, the other part you call it Y, the other part you call it Z. Is that okay? So that you have your generator, first generator, you raise it to the first part, and the second generator, you raise it to the second part, and then the other generator, you raise it to the third part. So it's that hexadecimal hash that you get, that you divide into those bits. So they could be 3 bits, they could be 5 bits, it could be even 20 bits, and so on. And those are the ones we use. Yes. Yes. So when I get this, after I've divided this into 3 bits, and the group, I get the generators of the group. The group gives me the generators, how many they are. Is that okay? I take those generator, then I raise it to these elements. I raise it to these elements that I've cut, the ones that I've cut. Is that okay? And then after adding the result, what I get, I reduce it mod n. When I reduce it mod n, I get an element of n. I get, when you reduce mod n, you get something which is smaller than n. Is that okay? Yes. You always get something which is less than n. And that is thing which is less than n is a member of the group. It's the member of the group. Yes. We'll also look at how to do multiplicative group, and that will make it even easier to make us understand. And then we will try to see if we can do it manually and see whether we can get the same result. Of course, we will then look at smaller groups and the smaller messages. Is that okay? But the thing is that this message, you will hash it. Once you hash it using SHA-256, what you get is 64 digits. 64, a number which is 64 digits, with 64 digits. Is that okay? Yes. Then this number that is 64 digits, you then divide it into bits. Divide it into bits. And each bit, you call one bit X, another bit Y, another bit. So depending on how many generators your group has. Is that okay? The group will have, may have 10 generators, but you only want to use 2 or 3 of those. Is that okay? It's not a must, you must use all the generators. You may want to use maybe 2 or 3 of the generators. So if you want to use 2 or 3, then that means your hexadecimal number, you cut it into those number of bits that you want to use. Okay, so now we explain how the code will then work. I imported SHA-256, and this is just to provide us a method for hashing. And then the number big integer or big unit. This one is used to handle arbitrary large integers. Because we'll be dealing with large integers. In fact, even the prime number is supposed to be large. So for you to do that, and of course the result will also be large. Is that okay? So for you to deal with those large integers, then you need to import this in your cargo domain. And also you need the num traits. And this one provides the ability to convert number types. So you want to convert from hexadecimal to a decimal, then this will assist you to give you that ability. To give that ability to do that. Otherwise, without it, it will not be easy for you to do that. Now, the first function, we had two functions. We had the main function and we had the hash to group function. The hash to group function, it has the input. Let me just go back to where the code is so that we look at it. Here is the code. We have the input here. Then we have prime, big unit, and then it gives the result. The result is also a big unit, and so on. So that is what I wanted to explain, the meaning of that bit. That's the bit I wanted to explain. Now, so input, at the input part, we have two arguments. The first argument that you can see is the input itself, and then we have the prime number. Well, that's what we saw there. So what does this mean? What is the use of this? This is what will be hashed. The input is what will be hashed using SHA-256. And then you have prime, reference of prime. So this prime here will then be defining the group. So if it's 7, it's telling us the group is mod 7. If it is 17, it's telling us the group is mod 17. So that is just a reference of the group we are dealing with. Then we have the part for SHA-256 hashing. We have the part for new. And then we have the input part. So the input is hashed using the hash update input. Then we have the hash output, and it's called hasha finalize. Hasha finalize. That is, let me just take you back then. So these are parts I'm referring to. Then update input, then the hasha finalize. So what that means is just after converting to the hexadecimal, this one is able to read that. This one is able to update the input. And this one is supposed to, and it is mutable here, it's mutable. So that means it's changing from time to time. It's changing from time to time as we store it inside this empty vector. Then we have this. This is the part that we're converting mod n. Mod n, you remember this is the remainder. So you take the hash from above and divide by n and get the remainder. This is what is happening at this point. So I've noted here that this is the point where hash to group is being reduced mod n, mod the prime number. reducing it to the prime number. That's the point we are doing that. Then of course you have the main function. The main function, as always, is just where we are inputting your values. So you want to input your message here, and then you want to input your prime number. You ensure that it's a prime number. Is that okay? Ensure that it's a prime number. Then it will print the result. Or inside here, in this, is that? This is the point where we are converting from hexadecimal to decimal. But now you want the generators. In this one, there are no generators in this additive group. The additive group, it doesn't necessarily require to use generators. There is a way you can do it without generators in the additive group. But when it comes to multiplicative group, it is a must that we have the generators. But for the additive group, it's not necessarily that we just, what we want in the additive group, we just want to, you can just convert the hexadecimal number directly to decimal without necessarily the use of generators. So that's what is happening here. But the example that I gave above, and you can see that example was, I had written here multiplicative group, the example. And so in the example of the multiplicative group, it's a must that then you must use the generators. The example of the multiplicative group. But for the additive group, you can convert directly from hexadecimal, decimal, without necessarily the use of the generators. So in this code, you do not require the generators. Yes. So just convert directly here. You can see the hash int. This is a point where we're just converting directly from the hexadecimal. This is hexadecimal is the base is 16. Is that okay? Hexadecimal, the base is 16. So converting it to decimal directly without we don't require the generators for this one. Yes, another question or contribution? Yes. Yes.
Once you get the group element, what's now what is the next step?
Once you get a group element, that is what you store, and it will be used later for other properties of cryptography. So this is what you use to do signatures if you want. This is what you use to encrypt if you want. We'll be encrypting the element, that group element, not be encrypting the message. So if we want to proceed with the cryptography after conversion, everything you'll be doing then will be done on this group element. Yes. So if you want to encrypt, that's what you'll be doing. You encrypt that group element. If you want to do signatures, digital signatures, they'll be performed on this group element. Yes, that's the next thing. Okay. So if there's not another question, maybe now we can have a few minutes. People have done something, and they now present the things they have done. It has been long, and I know that at least we tried to do a few things here and there. So we can use this opportunity to have one or two persons show us what they have been able to do. So we'll begin with our sisters. You know, they graduated. Yes, so after graduation, they must have done something now.